Now I want to go over the effect of pressure on solubility. Well, solubility is defined as the maximum amount of solute which can go into a solvent at equilibrium. For example, if we get salt, we are adding it to to water, let me say that. So how much is able to go into water before we start seeing crystals at the bottom? That is called solubility. So before we just start, just the maximum what you can add, maximum, before you start seeing crystals, that is called solubility. Now solubility is defined at equilibrium. So at a point of equilibrium, if you reach equilibrium, that means if you add anything more, if you add any more salt, you are going to see the salt on the bottom. But before you reach equilibrium, anything that you are going to add is going to be dissolving. And so at equilibrium, we call it a saturated solution. And before equilibrium, if you can add still more and more and more, that is called unsaturated solution. After equilibrium, that is going to become a supersaturated solution. Now, in this example, we have got first a substance which is at equilibrium, which is here. And by equilibrium, we mean, so we are talking about gas. We have got gas particles on top here. And the rate at which the gas particles are entering into solution, dissolving into solution, is equal to the rate at which they are also going out of the solution. And so we've reached a point of equilibrium. Now what happens when we reduce the volume? So we have changed the volume from the top here, V1 to V2. Well, we are talking of solubility. So when the gas enters into solution, that means it is soluble. Okay, it's entering into solution, and the rate at which it is entering is equal to the rate at which it is also leaving. In other words, they've reached a point where what is going up and what is going down is equal. So that is the point of equilibrium. Now the effect of volume. What happens when we change the volume? Well, we are looking at the effect of pressure, but pressure is related to volume. When we reduce pressure, according to the ideal gas law, pressure times volume is equal to number of moles times the universal gas constant times temperature. If we divide both sides by the volume, that will give us pressure being equal to number of moles, universal gas constant, temperature over volume. That means reduction in volume increases pressure. They are inversely proportional. And this is just direct because when you reduce the volume, for example, you have got this volume where you've got only 3 particles. If you make it even much smaller, but the same 3 particles are there, this will mean these particles will be able to collide more frequently. Okay, the frequency of collision is going to increase. They are going to collide more frequently. Because of that, because of the increased number of collisions, pressure increases, because pressure is only due to pressure, to the number of collisions, I mean. And so the reduction here in volume is increasing pressure. That is one thing that we can see from the ideal gas equation. So because of this, that means the particles which are here, the particles which are on top of the solution here, are going to have an increased pressure. So reducing volume increases pressure. Now this increase in pressure, what does it do? Well, because we've increased the pressure of these, that is going to make them to be forced now to enter into solution. Remember now, at this point we are at equilibrium because the pressure down was equal to the pressure on top. But if you increase the pressure, what does that do on the number of moles? Let's look at again the ideal gas law. Increasing pressure increases the number of moles. Those are direct proportion. So if the increased pressure which has resulted from the decrease in volume also increases the number of moles of gas particles on top of the solution, So because the number of moles has been increased, we know that increase in number of moles increases concentration. And so what we have just done is we have increased concentration. And we can even see this because pressure is going to be equal to, if we just get this term which is here, number of moles over volume, that gives us concentration, which is molarity, and then RT. That means if we increase pressure, we have increased the molarity. Now having increased molarity, that means we've increased the concentration on top. Okay, so particles are going to be reducing, they're going to be coming out of this region. In other words, we've just increased the number of moles of the particles on top. So to be able to reduce the number of moles, what is going to be happening is more of these particles are going to be going into solution to be able to reduce them because they've increased. And so that increases the rate at which the gases are entering into solution. So what have we just seen? We have seen that increasing pressure increases the concentration of these particles which are in solution. So this is actually stated by the Henry's law. What does it state? The Henry's law states that the amount of gas dissolved in a solution is direct proportion to the pressure of the gas above the solution. Amount of gas that is going to be dissolved here is direct proportion to the pressure of the gas which is on top of the solution. That is because if the pressure on top of the solution does increase, that increases the rate at which these are going to be going into solution. It increases the rate at which the gases are going to go into solution. Because we are having a lot dissolving in solution, we are increasing the concentration of what is in solution there. So basically this is what happens. And if we can consider carbonated drinks, for example, a common one I can give is Coca-Cola. Coca-Cola is carbonated, that is, the pressure inside the bottle, the carbonated drink, is going to be higher than the pressure which is outside. So we have sealed this. The pressure inside solution is higher. Why? The reason as to why we've kept the pressure inside the solution being high is because we want more carbon dioxide to dissolve into solution. So if we open this, what is going to happen is the pressure which is in the atmosphere is lower, and the pressure that we've used in solution is higher. That is why we have got more of carbon dioxide dissolved, because increasing the pressure of what is inside increases the amount of what has been dissolved. And so because of this, whenever you open the lid on a carbonated drink, there will be a fizzing sound that is going to be heard. That fizzing sound is due to the movement of the gas. So immediately you open this lid, the gas which is at high pressure is going to be moving out. It will be escaping much faster because we want to reach equilibrium with the atmosphere. And so a fizzing sound is going to be heard. Okay. Now we have just stated the Henry's law, and we've said it states that the amount of gas dissolved in a solution is proportional to the pressure of the gas above the solution. And we can put this in an equation. Amount of gas which is dissolved is proportional to the pressure above the solution. And this we can write it as K is equal to, we are going to put a constant K times P. Okay, I said K. C is equal to Kp, where this is called the Henry's law constant, and pressure is there. This is representing the concentration which is in moles per liter or moles per cubic decimeter. So that is it. That is the Henry's law. Now let's consider a question. What if we've been given a soft drink which is bottled at 25 degrees Celsius, which contains carbon dioxide gas at a pressure of, so we have got carbon dioxide gas at 25 degrees Celsius in a bottle, and carbon dioxide is bottled at 5 atmosphere. So this is the amount of carbon dioxide which is on top in a bottle. So we have got the carbon dioxide gas here on top, and we have kept it as 5 atmosphere. Okay, when we make this drink. Now, assuming that the partial pressure of carbon dioxide, so the partial pressure of carbon dioxide we've been told is equal to, let's say, 4 times 10 to the power negative 4 atm. Now, I want to calculate the equilibrium of carbon dioxide in the soda. Okay, just here in this solution, both before and after the bottle is opened. Now, what is the question talking about? Maybe let me be able to write that so that we can follow it well. So I'll write the question. A certain soft drink is bottled so that a bottle at 25 degrees Celsius contains carbon dioxide at a pressure of 5 atmosphere. Okay, over the liquid. So that is on top of the liquid that is inside the bottle. And assuming the partial pressure of carbon dioxide, the partial pressure that is of carbon dioxide is given as, okay, partial pressure of carbon dioxide in the atmosphere, not in the bottle, but that is in the atmosphere, is 4 times 10 to the power negative 4 atm. That is atmospheres. Want to calculate the equilibrium concentration of carbon dioxide. Equilibrium concentration of carbon dioxide in the bottle before and after opening it. And one value being given is the Henry's constant for carbon dioxide, which is K, and that is equal to 3.1 multiplied by 10 to the power negative 2 mole per liter atmosphere at this temperature, 25 degrees Celsius. Well, that is the question. Now, how do we even get to work it out? A certain soft drink, or does that even look like certain? This is N at the end. A certain soft drink is bottled so that a bottle at 25 degrees Celsius contains carbon dioxide at a pressure of 5 atmosphere over the liquid. The partial pressure of carbon dioxide in the atmosphere is 4 times 10 power negative 4 atmosphere. Calculate the equilibrium concentration of carbon dioxide before and after opening the bottle. Now, before opening the bottle, first let's calculate. We know that concentration is given by Henry's law constant multiplied by the pressure. Okay, and the Henry's law constant here is 3.1 multiplied by 10 to the power negative 2 mole per liter atmosphere, and this is multiplied by the pressure. The pressure of carbon dioxide in the bottle just above is 5 atmosphere. So you can see that the ATM and the ATM cancels out, so this is going to give us 0.16 mole per liter. This is going to be the concentration. So this is the concentration of carbon dioxide in the bottle. Okay, so when the bottle is open, the carbon dioxide in the soda is going to reach equilibrium with the atmosphere. We can see that the atmosphere has got this pressure of carbon dioxide, but this is the pressure of carbon dioxide in the bottle. So this is the pressure of carbon dioxide at equilibrium before the bottle has been opened. But at equilibrium, when the bottle is opened, what will be the concentration of carbon dioxide? And how do we get to calculate that? So the concentration is going to be equal to, so we have got the n is constant. We are again using K times P, because when you open the bottle, the carbon dioxide is going to reach equilibrium with the atmosphere. So it will be the pressure of the atmosphere after opening the bottle. Henry is constant, that is 3.1 times 10 to the power negative 2 multiplied by the partial pressure of carbon dioxide in the atmosphere with which it is going to reach equilibrium, which is 4 times 10 to the power negative 4. And this is going to give us 1.2 times 10 to the power negative 5 mole per liter. So this is going to be the concentration of carbon dioxide after the bottle is open, and then this is when the bottle is closed. So you use the pressure for the internal carbon dioxide, and this is for the external carbon dioxide. Well, thank you so much for watching. That is going to be all for this video. Stay blessed.